Go over Chapter 14, Practice Part 1. First of all, I am giving you here a strategy to assign oxidation number. When assigning oxidation number to the elements in a substance, take a systematic approach. Ask yourself the following question. First of all, is the substance elemental? If the answer to this question is yes, then you will use Rule 1. Question number 2. If the substance is ionic, are there any monoatomic ion present? If you answer yes, then you will use Rule 2. Question 3. Which elements have specific rules? You're going to look at Rule 3 for that. And then, which elements do not have rules? And then you will use Rule 4 to calculate this. Okay, so let's look at the first problem here. Give the oxidation number of each kind of atom or ion. So, Cl2. Is Cl2 elemental? Yes, Cl2 is the elemental form of chlorine, so we're going to answer yes at question 1. Therefore, we'll be using Rule 1. And if we're using Rule 1, what is the oxidation number for elemental substances? 0. So the oxidation number of Cl in Cl2 is 0. Question B. Is the substance elemental? No, it's a compound made of hydrogen and oxygen. 2. Is the substance ionic? No, H2O is covalent. Going to the third question. Which elements have specific rules? Well, per rule number 3, we know that oxygen has an oxidation number of -2, so that's rule number 3. And we know as well that hydrogen has an oxidation number of 1. So this is rule number 3 as well. Question C, NaCl. Is the substance elemental? No, it's a compound made of sodium and chloride. 2. Is the substance ionic? Yes, it's an ionic compound made of 2 monoatomic ions. It's made of the sodium ion, Na+, and the chloride ion, Cl-. Therefore, we'll be using rule number 2. And rule number 2 tells you that the oxidation number is the same as the charge of the monoatomic ion. Therefore, Na will be +1 and Cl will be -1. Question D. NaOCl. Is the substance elemental? No, it's a compound made of sodium, oxygen, and chlorine. 2. Is the substance ionic? Yes, this substance is ionic, and if you recall your naming from chapter 5, NaOCl is actually sodium hypochlorite. Sodium hypochlorite is made of the sodium ion, Na+, and the hypochlorite polyatomic ion, ClO-. Are there any monoatomic ion present? Yes. Here is the sodium, which is your monoatomic ion. Therefore, per rule number 2, this will have an oxidation number of +1. And then what do we have? Well, obviously, hypochlorite is a polyatomic ion, so we have to move on. Is there any specific role that the elements have in the compound? Well, yes, per rule 3, we know that oxygen is -2. There's no rule for chlorine, therefore we're going to be using for chlorine, we're going to pose chlorine as X, and we're going to use rule 4. Rule 4 states that the sum of the oxidation number of a compound is equal to 0 for a neutral compound. Sodium is +1, oxygen is -2, chlorine is unknown, and the sum of these oxidation numbers should be equal to 0. Therefore, +1 - 2 - 1 - 1 + X equals 0. and we're going to add +1 on each side. Therefore, X is equal to +1. And the oxidation number of chlorine in sodium hypochlorite is +1. We can use the changes in oxidation numbers to determine which elements are oxidized and which are reduced in the following reaction, and then we will identify the oxidizing agent and the reducing agent. So let's do it. We already did NaOCl, so I'm just going to copy the result from the previous question. Na was +1, O -2, Cl +1. Cl2 was 0. Here, H was +1, O -2, NaCl +1, -1. We still need to do HCl because it's something that we haven't done previously. Well, in HCl, it's not elemental, it's not ionic, but we have a specific rule. We know that H is +1, and we know per rule 4 that the sum needs to be equal to 0. Therefore, Cl will be -1, since +1 - 1 equals 0. So now that we have all our oxidation number for all the atoms or ions in this equation, we will be able to determine which one are oxidized and which one are reduced. Remember that the elements that are oxidized will see their oxidation number increase between reactant and products, and the elements that are reduced will see their oxidation number decrease between the reactant and the product. So let's look at it. Observe that the oxidation number, we can keep going one by one. The oxidation number of sodium doesn't change. The oxidation number of oxygen doesn't change. Shouldn't have used orange. Let's use another color like purple. Oxygen is -2 here. Oxygen is still -2 here. Let's take a look at the chlorine now. Well, we have the chlorine here that is +1 on the reactant side. And now the chlorine is -1 on the product side. Therefore, we can observe that the oxidation number of chlorine decrease. Therefore, chlorine in NaOCl is reduced. We're going to keep going. And now we can take a look at H. H is still the same. And now we're going to take a look at Cl being -1 in HCl. And Cl becomes here 0 in Cl2 in the product side. Therefore, for this Cl here, I observe an increase in oxidation number. The oxidation number of Cl increase. Therefore, Cl in HCl is oxidized. Sorry. Problem 2. Oh no, hold on. We have to identify the oxidizing agent and the reducing agent. Just remember that if Cl is reduced in NaOCl, it's because NaOCl is the oxidizing agent and responsible for the oxidation of Cl in HCl. And Cl is oxidized in HCl, and it's due to the fact that NaOCl is the oxidizing agent. Oops, sorry. And we have here HCl being the reducing agent. Okay, so HCl is responsible for the reduction of Cl in NaOCl, therefore HCl is the reducing agent. NaOCl is responsible for the oxidation of Cl in HCl, therefore NaOCl is the oxidizing agent. We can keep going with problem 2. Give the oxidation number of each kind of ion or atom. Carbon here is elemental. We're going to use rule 1, therefore oxidation number 0. Sulfuric acid, H2SO4. So how do we do this one? It's not elemental. It's not ionic. We have specific rule for some of the elements here. We know that H is always +1 per rule number 3. And we know that O is -2. This is per rule number 3 as well. We're going to pose the sulfur I being an unknown because there's no rule for sulfur. And therefore, we're going to use rule 4 to calculate the oxidation number of sulfur. Okay, so what is happening here? We have 2 hydrogen, 1 sulfur, 4 oxygen, and overall, the compound is neutral. Therefore, 2 times the oxidation number of hydrogen plus X, we don't know the oxidation number of sulfur, plus 4 times the oxidation number of oxygen should be equal to 0. We're going to solve for this equation. 2 plus X minus 8 equals 0. And therefore, we get X minus 6 equals 0. Add plus 6 on each side. X equal plus 6. So the oxidation number of sulfur in this compound is plus 6. Then we have carbon dioxide. Carbon dioxide is a covalent compound. Therefore, it's not a substance, it's not elemental, and it's not ionic. Specific rule, yes. Oxygen is -2. We're going to pose X as the oxidation number for C. Solving for the oxidation number of C using rule 4, the sum of the oxidation number is equal to 0. Therefore, C plus 2 times O equals 0. Oxidation number of C is unknown, X. Oxidation number of O is -2, so 2 times -2. X minus 4 equals 0. Add plus 4 on each side, and you get that the oxidation number of C in carbon dioxide is plus 4. Then we have sulfur dioxide. Again, elemental, no, it's a compound. Ionic, no, it's covalent. Rule number 3 give us -2 for O. We don't know S. The oxidation number of S is unknown, X. Therefore, we're going to solve for S plus 2 times O equals 0. Oxidation number of S unknown. 2 times -2 equals 0. X minus 4 equals 0, plus 4 on each side. Therefore, the oxidation number of S in SO2 is plus 4 as well. Now that we have this, I can go down and just write down all the oxidation numbers. 0 here, plus 1 for H. Was it plus 6 for S, minus 2 for O? Plus 4 for C, minus 2 for O, plus 4 for S, minus 2 for O, plus 1 and minus 2. We did H2O in the previous problem. Notice that you disregard the coefficient and you disregard the subscript when you write down the oxidation number. By convention, I write the oxidation number underneath every compound. And now we're going to identify. Okay, so let's see. We have carbon here 0, carbon here plus 4. Therefore, the oxidation number of carbon increase and carbon is oxidized. Keep going. What do we have next? I have H that is plus 1 here, H that is plus 1 here. H remain unchanged, so it's neither reduced or oxidized. I have S here that is plus 6, S here that is plus 4. Therefore, the oxidation number of S decrease from plus 6 to plus 4, and S in H2SO4 is reduced. Let's keep going and see. O is -2 here, -2, -2, -2. All remain unchanged, therefore O is neither oxidized or reduced. Now that we have this, we need to determine the oxidizing agent and the reducing agent. The carbon is oxidized. What's responsible for the oxidation of carbon? H2SO4. So H2SO4 is the oxidizing agent. In H2SO4, S is reduced. What's responsible for the reduction of S in H2SO4? The carbon. Therefore, the carbon is the reducing agent. Let's go to the back of the page now. Calculate the oxidation number of chromium. So what we're going to be looking for in these different problems is the oxidation number of chromium in each of the following. First compound, Cr2O3. I'm going to bring back memories from chapter 5, naming, because actually naming is going to be very helpful in this case. You remember when we had here, we have the chromium that is a transition metal with a variable charge. Well, when we name compound, the Roman numeral we were using in parentheses after the name of the metallic ion is actually the same as the oxidation number, okay? So let's just forget about this for now. And then if we use the different rules, we know that oxygen here is -2, and there's no rule for chromium, so I'm going to say that chromium is unknown and is X. Per rule 4, you remember that the sum of the oxidation number is equal to 0 for a neutral compound. Therefore, 2 chromium plus 3 oxygen is equal to 0. Oxidation number of chromium is X. Oxidation number of oxygen is -2, should be equal to 0. 2x minus 6 equals 0. I'm going to add 6 on each side. So I get that 2x equal plus 6. And now I'm going to divide by 2 on each side. And I get that x equal plus 3. Therefore, the oxidation number of chromium in Cr2O3 is plus 3. Okay? Mean that the chromium carries a positive 3 charge because this is a ionic compound made of 2 monoatomic ion, the chromium 3 ion, and the oxide ion. And by the way, this is why this compound that is formed by 2 chromium 3 plus and 3 oxide ion is named chromium 3 oxide. Notice that the Roman numeral here is the same as the oxidation number right there. B, Na2Cr2O7. If you recall your naming from chapter 5, this is sodium dichromate. It's made of the sodium ion and the dichromate ion in a 2:1 ratio. Therefore, if we use the rule, these will be +1. It's a monoatomic ion. This one is unknown, no rule. So I'm going to use rule number 4 to determine it. And per rule number 3, oxygen is -2. Again, we're going to use rule number 4. The sum of the oxidation number is equal to 0. So we have 2Na plus 2Cr plus 7O equals 0. Oxidation number of Na is +1. 2 times X, because we don't know the oxidation number of Cr, plus 7 times -2, and this is equal to 0. -2 being the oxidation number of oxygen. Therefore, +2 plus 2x minus 14 equals 0. 2x minus 12 equals 0. So again, we have 2x minus 12 equals 0. Add 12 on each side. Get 2x equal plus 12. Divide by 2 on each side. And I get here plus 6. So in Na2Cr2O7, sodium dichromate, the oxidation number of chromium is +6. For C, what is C? Well, C is here. That's the chromium 2 ion, if we were to name it per chapter 5. So we're going to use rule number 2 that states that the oxidation number is equal to the charge of the monoatomic ion. Therefore, the oxidation number of chromium here is going to be +2. Finally, D, chromate. So we have to remember what's chromate. Chromate is actually CrO4 2 negative. Chromate is a polyatomic ion. We're going to use the rule and everything we know here. We know that oxygen is -2, chromium is not determined, so it's going to be X, but we have to be careful. This is not a neutral compound. This is an ion that carries an overall charge. Therefore, when we're going to use rule number 4, and we're going to do that, the oxidation number of Cr plus 4 times the oxidation number of oxygen is equal to the overall charge. So here, it's equal to -2. Okay, chromate is not neutral. It carries a 2 negative charge. Now we can solve. X for chromium, 4 times -2 for oxygen equal -2. X minus 8 equal -2. Add 8 on each side, and you get that X here is equal to +6. Therefore, the oxidation number of Cr in chromate is +6. So here, what I wanted you to pay attention to is that we can actually have different oxidation number for the same element. Chromium could be +3, could be +6, or could be +2, depending on the substance it's involved in. Question number 4, type of redox reaction. Rewrite this metal displacement reaction, also known as single displacement, as complete ionic and net ionic equation. So you're given the balanced chemical equation. You're actually given here what we call the molecular equation. Okay, and again, it's balanced. You have the coefficient, you have the state of matter, you have everything you need. To write the complete ionic equation, you need to remember that anything that is, in the aqueous state will need to be dissociated, okay? And anything that is not in the aqueous state, and I'm going to circle it, will remain the same, okay? So I'm not going to touch to the aluminum, it's solid. I'm not going to touch to the copper, it's solid, but I'm going to dissociate the copper to sulfate. So what is CuSO4 made of? It's made of Cu2 plus and SO4 2 minus ions, but be careful, there's a 3, and the 3 distribute to each ion. Therefore, it's going to be 2Al solid plus 3 Cu2 plus aqueous and plus 3 SO4 2 minus aqueous. Forms what? The 3 copper solid, don't touch it. Plus, we're going to dissociate as well the aluminum sulfate, but here be careful, we have 2 of the Al3 plus ion and 3 of the sulfate polyatomic ion. So this is here your complete ionic equation. In this equation, we need now to identify the spectator ion. Spectator ions are the same on each side of the equation. So here are the spectator ions. The sulfate polyatomic ion are the spectator ion. And in order to write the net ionic equation, we're going to remove them. And what is left for the net ionic equation is therefore, again, we're going to remove them to write the net ionic equation. So we have left 2Al solid plus 3 Cu2 plus aqueous gives 3 Cu solid plus 2 Al3 plus aqueous. Here is your net ionic equation. Problem 5 asks you the opposite. Problem 5 gives you the complete ionic equation. How do I know this is the complete ionic equation? It's because I can observe that I have spectator ions present. So if I have spectator ions present, it means that this is the complete ionic equation. I see ions and the spectator's ions are present in the equation. In the molecular equation, I will need to put back the aqueous ion together into an ionic compound. So what I have here, the combination between Au plus and F minus, so it's AUF and it's in the aqueous state, and I have two of them. Here, my iron solid was already there. And what am I forming? Well, I observe here that I have another compound made between iron 2 and F minus in a 1:2 ratio. So this compound is FeF2 aqueous, and then I have my solid gold. So here is my molecular equation. If I wanted to write the net ionic equation here, what would I do? I will take away the fluoride ion from the complete ionic equation, and the complete ionic equation minus the spectator ions will give me the net ionic equation, and my net ionic equation would therefore be Fe solid plus 2Au plus aqueous gives Fe2 plus aqueous plus 2Au solid. I hope this helped you understand chapter 14 better. And the next worksheet, part 2, is coming after that one. Let me know if you have any questions. Bye-bye.